So I was asked to talk about the animal models and how we use those in the development of RNAi, since RNA interference is becoming a pretty popular theme in HBV, and you're going to be hearing more about it. So the thinking was you might be interested. Disclosures, I am an employee of Arrowhead, obviously, so I have an embedded interest here. So we got interested in HBV back around 2010 or so, and we're a public company, so for us to be able to do research, we actually have to convince people that they should invest in us to allow us to do that. And at the time that we got interested in HBV, everybody that we talked to only cared about hepatitis C. And even though from a research perspective, we thought hepatitis C was over, from a investor community perspective, they were really excited. So we sort of oversimplified HBV to try to get through to them and to get them to listen to us. So we created this rather well oversimplified cartoon. And what we were basically saying is, look, everyone knows that entecavir and tenofovir especially are very good nukes, and if patients actually adhere, the likelihood is that after a few years, they're going to be undetectable or near undetectable with respect to viral DNA, which if you were talking about hepatitis C, people would think you had cured the virus, but HBV is not Hep C, and in fact, being a DNA virus, CCC DNA really sort of dominates, and I think as all of you are aware, the nukes really don't do much at all for CCC DNA. So in fact, you can have no measurable DNA in the circulation. I know that doesn't mean it's not there, but you can still have very high levels of circulating viral proteins. And as Stephen had just said, there's always been this belief that antigenemia has a lot to do with especially the peripheral immune suppression. So we thought we could convince people that if we could lower this circulating antigenemia, that perhaps we could make some real headway against the virus. Now, in fact, what's neat about RNAi is that you've got the ability to potentially knock down the entire transcriptome. So as we were just hearing from Stephen, people are getting really interested about core, they're getting interested in X. People are interested in trying to make the nukes work better by attacking polymerase and the like. And the interesting thing about RNAi is it's basically a combination drug in and of itself, in that it does all of that, in addition to working on circulating antigenemia. So this cartoon maybe wildly oversimplifies things now that we've gotten more interested in all of these steps in the pathway. I'm not going to repeat this slide, which you just got walked through, except to say one important thing, and that is that when this cleavage goes on, it's consumptive, of course, for the RNA of interest. It is not consumptive for this small interfering RNA. And in fact, these small interfering RNAs can stay loaded in risk for days or even weeks. So it's possible that a single RNAi molecule here can actually wind up leading to tens or maybe hundreds of RNAs being degraded over time. So it's a catalytic process, and it's not a consumptive process. And the thing that the pharmaceutical companies have gotten really pretty good at is figuring out how to make these molecules very stable, very competitive for risk. And that's why we get these extremely long durations of action. So Professor Yoon will be showing you single dose data with ARC-520 and show you weeks of duration of effect. And it's because we're very good now at making these molecules stable in the cytoplasm, stable in risk, and essentially in some ways out-competing the endogenous siRNAs. So what's neat about HBV is that it has this very compact overlapping genome, such that it produces 5 different transcription products of 2 of 3.5 kilobase length, 1 of 2.4, 1 of 2.1, and the X transcription product here, which is about 0.7 kilobases in length. But all of them terminate at the same place. So in fact, if one of the neat things about RNA is siRNAs, they're very specific. So we tend to think about one siRNA knocking down one gene and only one gene, which of course makes it safe from an off-target sort of effect. But because of this overlapping nature of this genome, if you pick siRNA molecules in this area, you could potentially knock down all of the products of HBV. Now, if you picked one over here, all you would get would be the 3.5 kilobase transcripts. Or if you pick one here, you'd get the 3.5s and the 2.4. Here, you'd get all except for X. But you've got the potential that you can knock down the entire transcriptome with a single siRNA molecule. This replays the process by which we discovered ARC-520, but this is also the process that the industry would essentially follow for any gene, or in the case of HBV, for trying to attack the transcriptome. So the process was initially done in silico. They went to GenBank, they harvested all of the sequences in GenBank, and they looked for areas of conservation, with the rationale being that over generations and over millennia, if there were certain areas of the HBV that had been tightly conserved, the virus probably couldn't get by without those. So they started with all these fully conserved regions across all these different sequences in GenBank, something like 2,500, and then these are 19 to 21 mers, so the computer just spits out basically all of the possible 19 to 21 mers across those conserved regions. And then there are a few things that you screen out. So you screen out any homology with human genes. In this case, we're dealing with a virus. So you screen out any cross-reactivity with human genes. You screen out any that may have microRNA type activity, things that the industry has learned how to do. And in the end, we went from probably several thousand possible RNAs down to 140. And the one thing that you learn early in this business is that the computer really does a poor job of predicting which RNAs will work. And if you go screen them in vitro in a reporter assay, you see some of the siRNAs, even though they have perfect homology, make for lousy siRNA molecules, are just not very good at loading into RISC and cleaving. And then inevitably you get down to 4 or 5 or 7 of them that actually are quite potent. We took the best 4 and we actually screened them in vivo, and I'll show you a little bit of that data. And shown here are these the RNA transcripts. So you can see the best 2 were here very distal in the molecule, such that they picked up all 5 of the RNA transcription products for HBV. Our next best 2 were actually here in the S domain, so they would knock down everything but X. So they would not get X, but they would get everything else. They get core, pre-core, they get the pregenomic RNA, et cetera. And of course, S and E as well. So ARC-520 consists of 2 different RNAs. So I just showed you those 2 very distal at the 3' end. It's got both of those siRNAs. They're conjugated to cholesterol to make them trophic for the liver. What's different about the Arrowhead basic concept is we also include an amphipathic peptide that we mask the amines and then target this peptide to the liver with N-acetylgalactosamine. So we target the acetylglycoprotein receptor in the liver. When this peptide gets into endosomes and the endosomes start to acidify, the masking falls off, this becomes amphipathic, and it allows the RNA to escape into the cytoplasm. You know, early on in the evolution of this world of RNAi, people got very excited, huge investments were made, and then they figured out they actually could not get the RNA molecules into the cytoplasm. They'd get into the endosome and they'd get eaten up. This was our way of solving the problem of how do you get the RNA out of the endosome. Other people have now solved this problem that by making the RNA so resistant to degradation that they sort of outlast the endosomes, and with the trafficking into lysosomes, et cetera, there's enough leakage that you get a few of these molecules into the cytoplasm, and that's enough to get deep RNAi. But our process goes like this. This is not a complex. These do not associate in any way. They get to the liver independently. So now I'm going to talk about the animal models. I haven't given you that background. So as mentioned by Dr. Laccarnini, and I'm sure as most of you all know, there's been a lot of work historically done with the duck hepatitis B virus and the woodchuck hepatitis B virus. They bear a lot of similarities to HBV, but they're not the same, and in fact, they don't have enough homology for at least our RNAi molecules to work. As I said before, the thing about siRNA is it's remarkably specific. So in fact, you know, most people who work in this field, or I'm not aware of anyone who's actually developed any siRNAs against these viruses, since we're interested in HBV. The mouse models have, as is not uncommon, have really been the workhorses in doing this research, and there are several of them. The thing that tends to be typical of these top three anyway, and I'm going to go through them in more detail, is they all use full-length HBV DNA. So that the goal here is really to try to get the full replicative cycle if you can. I'll talk about the plasmid model, but again, it's a full-length DNA. Same thing with the adeno-associated viral deliveries or adenovirus deliveries. Again, you're trying to express full-length HBV DNA. Both of these use immune-deficient mice. The transgenic mouse model is a transgene. It has the advantage that 100% of the mouse hepatocytes have the HBV DNA and express the HBV DNA, which gives you some advantages. And then there are chimeric mouse models that have both human and mouse hepatocytes, at least the most common models, and therefore you can actually infect these. Finally, the best model of all is the chimpanzee. We learned a tremendous amount over the last year and a half in a study we did in 9 chronic HBV-infected chimpanzees. Unfortunately, they're now off limits, so that's probably the last great HBV chimpanzee study. Fortunately, we got a lot out of it. So first of all, the plasmid HBV model, basically we incorporate the full-length HBV DNA into a plasmid. This is injected at high pressure through the tail vein into the liver. What happens is about somewhere as few as 5, but as many as 20% of the hepatocytes will become infected by this model. It's just a sheer mechanical force, transfection. I'm not sure, maybe Stephen didn't say it, but the mouse is not a host for HBV because it does not have the NTCP receptor. So you can inject mice with HBV, they will not become infected. Also, I've heard, I haven't seen the work, but I've heard as well that even if you knock in the receptor into mice, they still won't become infected, and I believe they have difficulty actually transporting the nucleocapsid into the nucleus. So they seem to have some other lesions besides just missing the NTCP receptor. But when we do this, what happens is after about a month, you'll get a stable level, a relatively stable level of viral replication. You'll make all the antigens, you'll make virus and secrete virus into the circulation, and then we can use that for assay. And this shows you what we got with our two siRNAs that are included in ARC520. So the first thing to notice here is you see this, this is the isotonic glucose treated line, and you see that there's this slow slope down. Because the mice don't reinfect, and because they cannot resupply the nucleus, basically as hepatocytes die, you lose expression. But it's very slow because you don't, this is not an inflammatory state, so you don't lose hepatocytes all that quickly. But this is something you always have to deal with this model. But then, as you can see with RNAi, you get a very fast and very deep reduction in the viral transcriptome. So surface antigen falls by over 3 logs, DNA basically to the level of detection, E antigen to the level of detection. So it's really a good way of sorting out your potential triggers. And you can also see here the duration is really quite long. So this is that point that if your selection gets you good RNAi triggers, you can have very long duration of effect from a single injection, which is something that's very different relative to most pharmaceuticals. The transgenic model is just a transgene, again, with the full-length, fully competent HBV DNA. These mice are immunocompetent, and because of that, they make antibodies to surface antigen, so you can't measure surface antigen in the circulation, and you also cannot measure viremia. But they're really terrific for looking at what's going on in the liver with respect to RNA and also with respect to your DNA intermediates, your single-stranded DNA, as well as your relaxed circular forms as well. So this shows you what we got with ARC520. Interestingly enough, you didn't have complete loss of the 3.5 kilobase RNA, while you pretty much could not see any sRNA, and you couldn't see any of the DNA intermediates. The transgene, of course, is not affected because we're not making that go away. That's stable. This is from one of our chimpanzees, and this is shows the power of the chimpanzee model, which unfortunately is now gone. But this was an entecavir run-in, and you can see during the entecavir run-in the DNA fell quite rapidly, as you would expect. But S antigen was very little changed. E antigen was very little changed. Then we added ARC520 to the entecavir. You get a very rapid drop in S. You get a rapid drop in E. The DNA shows some decline also, but it tended to recover at the end of the month. You notice initially this is ALT. You get a reduction in inflammation. And then something very interesting happened. While the DNA was falling, while the E antigen was falling and the S antigen was falling, this chimp actually flared. So this was a therapeutic flare. Following the therapeutic flare, you no longer have any measurable DNA or E antigen. The S antigen continued to fall, and then we lost the ability to keep treating the chimps. They went off all therapy, and in this particular chimp, when he went off therapy, the DNA starts to come up, the S antigen comes up, and you can see the ALT started to rise. Didn't go above the upper limit of normal, but there was clearly a change here. And when that happened, there was an immune control such that rather than returning all the way to baseline, the DNA stayed down about 5 logs, the S antigen stayed down 1.7 logs. So you saw a recovery of immune function. And this was associated with CXCL9 and CXCL10 spikes, as well as gamma interferon. It's really a pity to have lost this. So going through the advantages and disadvantages of the models, For ducks and woodchucks, probably not useful for RNAi because there's no real sequence homology that you can take advantage of. It's not human HBV, and in fact, these models have sometimes incorrectly predicted therapeutic response that hasn't carried over into humans. The mouse models have been quite useful, but they don't produce cccDNA. They lack the viral uptake, so you can't get the full replication cycle, but they will produce viral particles. They will produce all the antigens. The PHBV and adeno-associated adenoviral transfection models do allow you to see what's going on with respect to viral RNA, DNA, surface antigen, and E antigen in the serum, but they are immune deficient, so you can't study the immune system, and there is this gradual decline. Whereas the transgenic models, it's stable replication, but unfortunately you can't really tell what's going on in the circulation. And it's the mouse immune system which doesn't really tell you what's going on from a human perspective. The humanized mice are interesting. The older models have been a bit problematic in that they tend to sort of be clonal expansions, so they have abnormal architecture which can create delivery problems for some of the drugs that you might want to look at. Most of these are immune deficient, but we're starting now to see some chimeric humanized livers and humanized immune systems in mice, which may really be pretty good models. It's early days. These are very expensive, very time-consuming to produce. The chimps were the best model of all, but now they've been declared off limits. So my last slide, in summary, all cccDNA-derived HBV transcripts can be attacked with a single siRNA molecule because they share the same poly-A termination site, which is a special attribute. So you really can create a drug that attacks the entire virus at the level of the hepatocyte. The chimpanzee is clearly the best model, but it's no longer available. The mouse models are quite useful for RNA drug development, but not really for studying the disease per se. The newest models could prove interesting, and they might actually let us try to understand what's going on in a humanized situation, but it's early days. Thank you very much.